Today we're going to talk about integrals. Integrals and what they are and how to find the area under functions using them. First of all, an integral is notated somewhat like this, like an elongated kind of S. And we can use what an integral is. So an integral is the sum of an infinite amount of infinitely small elements. And we can use that to find the area under a function. So how do we go about doing that? So first, we can see this. So if we're given a function such as this, and this function, we can name it fx, and we're given this boundary, and we're asked to find the area, this boundary here. We're asked to find the area under this boundary. We can go about doing that. We can get approximate of the area by dividing this boundary up into pieces. So we have two pieces here. We can name these points x1, x2, and x3. And actually drawing rectangles, so we can draw these rectangles. Now we know how to find the area of rectangles pretty easily. It's just the width times the height. So using this, we can approximate the area. So the height of the first rectangle is f of x1. So f of x1 times the width, which is x2 minus x1. And we add that to the area of the second rectangle, which height is f of x2, and the width is x3 minus x2. This gives us an approximate area. But what we can note that this region here, and this region here are not covered in our approximation. So to get an exact answer, we can first note that if we're given this function all over again, the same function, f of x, but this time, and the same boundary, but this time we divide it into more than two pieces. We divide it into three pieces, and we denote the same thing: x1, x2, x3, and x4. And this time we draw more rectangles, so one rectangle, two rectangle, and three rectangles. And we can approximate the area again. So this would just be f of x1 times x2 minus x1 plus f of x2 times x3 minus x2 plus f of x3 times x4 minus x3. This also approximates the area, but it approximates it much better than the approximation we had here. Less of the space is not accounted for, because we had this, and now we're accounting this extra rectangle's area. So we've noted that as the rectangles get smaller and smaller, and the number of rectangles gets bigger and bigger. As the number of rectangles approaches infinity, we get closer and closer to the exact area under the function. So if we have three rectangles as we showed, the area of those three rectangles would be f of x1 times x2 minus x1 plus f of x2 times x3 minus x2 plus f of x3 times x4 minus x3. And we showed that the amount of rectangles we have, as that increases, we get closer and closer to the area. So we said this can be much easier notated this way. So this, like, if we keep going, this can be much easier notated like this. Sigma has sum, and we have n as the amount of rectangles we have, and we have a dummy variable k equals 1. We can see that we have f of xk times xk plus 1 minus xk. So, but we want n to go to infinity, right? Because we want the amount of rectangles to get bigger and bigger. So what we actually write is sigma k equals 1 f of xk times xk plus 1 minus xk. But instead of n, we write infinity here. So as the number of rectangles goes to infinity, as it gets bigger and bigger, we get closer and closer to the actual area. So this equals the actual area. It's not an approximation, it equals the exact area of the function. Now we're left with this. This represents the area under a function. But this translates to an integral because we know that the integral is summing an infinite amount of infinitely small things. And this is what that's doing. We're summing an infinite amount of infinitely small rectangles, or infinitely narrow rectangles. So we can write this as the integral f of x. So say we're just dropping the subscript k, f of x. And this is delta xk, which can be written as dx, so with respect to x. And if we're given a boundary, x of n to x0, we can evaluate this integral. I'll show you how. So given the function f of x is equal to something like 6x squared plus 2x plus 3. We can write this down as the integral and say we want to find the area under this function for in the boundary 2 to 4. So we write 4 to 2, the limits, 6x squared plus 2x plus 3 dx. And how do we actually evaluate this? Well, all the integral is the antiderivative. It's the opposite of a derivative, and I'm not going to go into why this is, but this, just take it as my word. So the integral of this would be 6x squared. What would we need to differentiate to get here? We would need to differentiate 2x cubed to get 6x squared plus x squared plus 3x. And we can't forget about the constant of integration, plus c. This is the constant of integration. Now this comes there because the derivative of a constant is always 0. So no matter what this constant is, as long as it is in fact a constant, it'll be the same thing. So we write plus c there. And we write the limits like this. 4, 2. This equals that. That's how we find the integral. But how do we now... We have the general term, but how do we find it within the boundaries? Well, say 2x cubed plus x squared plus 3x plus c is equal to g of x. We name this function g of x. We would actually find the area by taking g of 4 minus g of 2. This equals the area. So we can do just that. G of 4 is 2 times 4 cubed plus 4 squared plus 3 times 4 plus c minus g of 2, which is 2 times 2 cubed plus 2 squared plus 3 times 2 plus c. This equals 64, so this equals 128 plus 16 plus 12 plus c minus 16 minus 4 minus 6 minus c. So as you see here, the c's get cancelled, and this always happens during integration and finding the area. Now this is equal to, we have 16 here, and with these 16s cancel, we see that. So we are left with 12, and we can, this is minus 8, so we would get 12, and then we would get minus 8, or plus 8, and then minus 2 would be plus 2. So we are just left with 128 plus 2 is equal to 130. So the area under this function between 2 and 4 is 130. And that's how you find the area under a function using an integral.